So last class we were working with complex numbers and operations of complex numbers, and we ended with a fraction or a division here, where we were dividing 5 minus 2i by the complex number 3 minus 5i. And what we did was we used the conjugate of the denominator. So remember, the conjugate of the denominator is the same real term, and it's the opposite imaginary term right here. And we're going to multiply by 1 in the form of 3 plus 5i over 3 plus 5i, distribute and simplify. All right, so just a couple quick reminders of this. When you're doing the product of negative 2i all the way to 5i here, just make sure you remember to multiply negative 2 and 5, make it negative 10, and don't forget about the I squared, okay? Remember, I squared is negative 1, so this term is going to become a positive 10. Down in the denominator here, same thing, negative 5i times positive 5i. This is going to become negative 25, I squared. Again, I squared is equal to negative 1, so this term becomes positive 25. These inner terms here will always negate each other to 0. They're always going to be opposite values. That's one of the reasons why we're using the conjugate, and we're always going to be left with a real number in the denominator. So this in red here is equivalent to the answer, but it's not yet in standard form. We have to have the real term plus or minus the imaginary term. So that we're just going to split it at the addition or subtraction sign, and we'll have 25/34 plus 19/34 I. So let's finish with this example here. Now this one contains a radical. Same process though, right? So what we're going to do is we're going to multiply by the conjugate of the denominator here, 5 plus I root 2. If you see me write it as 5 plus root 2i, it's the same thing. Just remember that I, if it's on the other side of the radical over here, it's not in the radical. It's just being multiplied to the radical. So we're going to go through and distribute all terms in the numerator to this numerator, and then same in the denominator here. And when I do that, it's a process. Take your time. Here, 3 times 5 is 15, and then we go 3 times I root 2. I'm going to express it here as 3 root 2i, just to keep the real coefficient separate from the imaginary unit here. Same thing with I root 2 times 5 root 2i. Remember, these i's are not inside the radical. And then lastly, again, don't forget to multiply the i's. Don't forget to multiply the radicals. So root 2 times root 2 is 2. I times I is I squared. So this term here becomes 2 times negative 1, which is negative 2 here. Denominator, same process. 5 times 5 is 25. 5 times I root 2 is 5 root 2i. Negative I root 2 times 5 is negative 5 root 2i. And lastly here, negative I root 2 times positive I root 2 leaves us with a negative 2. Now that's from the negative here and the positive here, and then I squared. So this term in the denominator becomes negative 2 times negative 1, or positive 2 there. Once you're here, combine like terms when you can. So we have 3 root 2i plus 5 root 2i. That's going to leave us with 8 root 2i's. And then in the denominator, these inner terms negate to 0. 25 plus 2 is 27. Almost done. Leave it in standard form. So we're going to separate the real from the imaginary here, and we're done. So this next example is something we didn't get to. And it looks super complicated. It's really not that bad. It actually involves working with a system of equations. So, you're going to focus on the left side first. And the left side, like we said earlier, we're going to group values here just to kind of identify portions of this equation for that. But here we have 3x minus 4i. And then plus, and then another grouped term or set of terms here, 2x plus y times I. Both of these are equivalent to negative 13 minus 5i. So if you think about this from a complex number perspective, this term that's grouped first here would be considered the real part of the complex number. This second group here, 2x plus y, would be considered the imaginary portion of the complex number because it's being multiplied by the imaginary unit I here. So the system comes into play when we associate that the real portion of the left side of the equation here is equivalent to negative 13, and the imaginary portion over here is equivalent to negative 5. And we're just going to set our system up, right? So seeing it from the perspective of a complex number, a plus bi, over here, same thing, a plus bi. So what we can do is we can say this portion right here is equivalent to negative 13, and this portion right here is equivalent to negative 5. Be careful with the red. We're just setting 2x plus y equivalent to negative 5. We're not including the I in this case. And then we're just going to start solving our system, right? So 3x minus 4y equals negative 13. 2x plus y equals negative 5. We're going to set the system up. So because both of them are already in standard form, I'm going to use the elimination process. I'm going to multiply the red equation here by 4 to make opposite coefficients for y. After doing so, and I add my equations, I'm going to end up with 11x here equals negative 33 on the right side. The y is simplified to 0. And now solving, I'm left with x equals negative 3. Once we have x equals negative 3, we're going to turn around and we can substitute this into either of these original two equations in the system we created. I'm going to work with the top one, no preference really. So 3 times negative 3 leaves us with negative 9, and then I'm going to solve this basic equation here. I'm going to add 9 to both sides, divide by negative 4, and now I'm left with y equals 1. So we're almost done at this point. And then we're just going to identify it as x equals negative 3, y equals negative 5. Now, if you go back and look at the question, it says find the real numbers x and y such that this equation is true. So here, really, you're just trying to find the values of x and y. You're not trying to express it in an ordered pair. Even though we used the system to solve this, our answer is not a point of intersection. Our answer is the values for x and y in this case.